So energy does affect matter, and so we need to have some definitions here because a lot of these words are used in everyday life. You might say, oh man, I just don't have much energy today. Well, that use of the word energy is different than what we use in science. So in science, we say that energy is anything that has the capacity to do work. If you have the capacity to do work, it's energy. Well, what's work, right? We think of work as being some perhaps not so pleasant activity that someone's going to give us money for, right? In science, work is a force acting over a distance. So if I take this acetone bottle and I push it across the bench, I did work. I exerted a force across a distance. You pick something up off the floor, you're exerting a force across a distance, it's work. So energy, the capacity to do work, force times distance. We also need to talk about what heat is. Heat and energy are not the same thing. They're very easy to confuse. Heat is the flow of energy caused by a difference in temperature, and we'll talk about that a little bit more. But energy can be exchanged between objects through contact. So when we have two objects of different temperatures, like your hand and the little hand warmer, there's an exchange of energy from the hand warmer to your hand. We can also have energy being exchanged through collisions. So think of energy as a quantity. It's something that can be possessed. I think of energy as being a lot like money. Okay, you can have money and you can transfer money to someone else. Heat and work are ways that an object can exchange energy with other objects. So energy is something you have. Heat and work are the movement of energy in one direction or another. So we have to talk about different kinds of energy. Kinetic energy. This is the energy of motion. When something is moving, it has kinetic energy. Thermal energy is a subcategory of kinetic energy. It's the energy associated with the temperature of an object. You feel the hand warmer and it's warm. It has more thermal energy than, say, the bench top that is at a lower temperature. So if you look at that hand warmer, whoever has it, is it moving? Who's got the hand warmers? Are they moving? He's got both of them. He's happy. His hands are warm. You know, if you set them on the bench, they don't move, right? They're just sitting there. So how can they have kinetic energy? Well, when you move them back and forth, you are giving them kinetic energy, but they have kinetic energy when they're sitting there because the particles in the solid are moving. Remember the analogy of the different states of students? Right now you guys are in the solid state. You're sitting in your chairs, right? But you're moving, right? So you do have kinetic energy. If I raised the temperature of my solid state students, you would just be jiggling around, maybe doing some chair dancing or something, right? You'd be wiggling more. That's kinetic energy. You're just not moving relative to each other. So the hand warmer, those individual particles are moving. That's the thermal energy. That's why thermal energy is a form of kinetic energy. We're also going to be talking about billiard balls. So when this white cue ball is moving across the table, it has energy due to motion, kinetic energy. When it collides with the purple ball, it does work on the purple ball and transfers its kinetic energy to the purple ball, and the purple ball shoots off and has kinetic energy. So that's transfer through collision. Any questions? We're flirting with physics here is what we're doing. The other broad category of energy is potential energy. This is energy that is stored in an object, or it's energy associated with either composition or position of the object. So here we lift the purple ball off the table. it has gravitational potential energy because it's elevated. We let the ball go, it falls. The potential energy gets transformed into kinetic energy. The ball picks up speed as it gets lower and lower. Its potential energy decreases as it falls. So potential energy can be due to position. It always makes me think of those old classic cartoons. They were always hanging pianos out of second-story windows. And inevitably, the ropes broke and landed on somebody, right? A lot of kinetic energy there. But potential energy before the rope breaks. Chemical energy is a kind of potential energy, but it's not due to gravitational potential energy. It's not due to a position of the substance being elevated. It has to do with the positions of the electrons and the nuclei, which are positively charged inside the atoms and the molecules. And so there's potential energy there because if you change something, there can be a lot of energy that's released. So here's the overview. Energy is the capacity to do work. We've got kinetic energy, that's due to motion. Thermal energy is a subcategory, that's energy associated with temperature. Bless you. Potential energy has to do with position or composition. Chemical energy is a subcategory of that. Here are some other types of energy. Electrical energy. This is a kind of kinetic energy. Electric current is a flow of electrons. It's electrons moving through a substance, usually a metal. That's kinetic energy. If you've ever gotten, stuck a knife in an electric socket, is there energy in there? Yeah, there is.
Did Dr. K do that?
Dr. K probably did that as a child. He probably did. He was a bit of a rascal. I didn't do anything like that. I was just a boring child, did whatever my mommy said. Pliers? Yeah. Paper clips, lots of different things. We talked about heat or thermal energy. Light, also known as radiant energy. This is kinetic energy associated with energy transitions within an atom. Does light have energy? Well, can you get a sunburn from the light being given off by the sun? Sure you can. You can feel the heat of the sun. There's definitely energy there. Nuclear energy is potential energy that's found in the nucleus of atoms. And then we've also talked about chemical energy. So any questions about the different types of energy? These are not the only kinds. There are others. We've talked about the law of conservation of mass. There's a similar law called the law of conservation of energy. Energy cannot be created or destroyed. It can be converted from one kind into another. It can be converted or transferred from one object to another, but it is not created or destroyed. So here you press down on a ball onto this spring. You're putting mechanical potential energy in here. You release it. The mechanical potential energy is transferred or transformed into kinetic energy as the ball shoots up in the air. When we're talking about energy being transferred, we need to define what we're transferring it from and to. And so we talk about the system and the surroundings.
I have a question.
Mm-hmm.
It's about the last slide. I apologize. So, if the ball is resting on the spring, there's no energy.
If the ball is just sitting on top of the spring, it doesn't really have a noticeable energy. The thing about energy is, what do you define as zero? Is something laying on the ground, does that have zero potential energy? Well, what if it's on a trapdoor on the second floor of a building and you open the trapdoor, it's going to fall? It does have potential energy. Well, what if it's on the ground but it's on a manhole cover and there's an opening underneath, right? So where do you define zero? But yes, the ball would have less energy, less potential energy if it's just sitting on top of the spring.
So
when it's pressed down, she's putting energy into it by doing work on the ball. Yeah. Yeah, energy has to go somewhere and it has to come from somewhere. It doesn't appear and disappear.
Otherwise, cars would be a lot more efficient.
Oh, yeah, definitely. So the system is whatever we're interested in. We can define anything as the system. You could define the Earth as the system. You could define one atom as a system, whatever you want. The surroundings are everything else. Technically, everything else in the universe, but most practically everything else with which the system can exchange energy. Okay. And then we look at the exchange of energy between the system and the surroundings. It's pretty much impossible to measure energy, but we can measure energy changes. And so that's what we do. Conservation of energy means that however much energy is gained by the system is lost by the surroundings, or vice versa. Here we have an illustration of energy transfer. So think of these as like fuel gauges. Here's the system energy, it's half full. Here's the surroundings energy, it's a quarter full. After the transfer of energy, the system is a quarter full and the surroundings are half full. Because all of the energy that left the system went to the surroundings. Any questions? Well, we have to be able to measure energy, so we need units. We talked about this a little bit on Tuesday. Kinetic energy is proportional to the mass and the volume. Kinetic energy is 1/2 the mass times the velocity squared. I said volume, velocity. It's a small v, capital V is volume. The SI unit of energy is the joule, Joule, abbreviation capital J. It's a relatively small unit. Just kind of for reference, a 100-watt light bulb in 1 hour of burning would use 3.16 times 10 to the 5th joules. That's a lot of joules. It's a small unit. We can apply the metric prefixes to this unit. The most frequent one we use is kilo. A kilojoule is 1,000 joules.
We need to remember the kinetic energy.
You don't need to memorize this equation. I stick it up there just so that we get some understanding of what's going on. But we're not going to do any calculations with that particularly. So the joule is defined as the energy needed to move a 1 kilogram mass a distance of 1 meter. Remember we said that energy was a force applied over a distance. No, that was work. Sorry. Work has units of energy, which is confusing. Anyway, it's a Newton meter. A Newton is a kilogram meter per second squared, so when you multiply this out, it'd be a kilogram meter squared per second squared. That's the one that was giving me trouble on Tuesday. We were trying to cancel out those units in the root mean square velocity equation. So that's a joule. You do not need to memorize this business, but some of you might be interested in that. A calorie, we use the unit calorie in chemistry a lot. A calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. That's how it's defined, and so that the 1 there is exact. The relationship between joules and calories is this one. You don't have to memorize that, but it wouldn't hurt. I will give that to you, though, if you need it. A calorie is 4.184 joules, and that is an exact conversion. We are familiar with calories. We talk about calories in everyday life. Oh, it's a low-calorie dessert or whatever. The calories we're referring to there in terms of food are nutritional calories, or calories with a capital C. In terms of scientific calories, those are kilocalories. So 1 nutritional calorie would be the amount of energy needed to raise the temperature of 1,000 grams of water 1 degree Celsius. So to take a liter of water and increase the temperature by 1 degree. These are some conversion factors from your book. You might need to look them up. We won't use kilowatt hours very often, but you can do a conversion there. and we already talked about those. This is just, you know, kind of for your interest, the size of these things, right? So if you think about running a mile, right? How much energy is that? Well, that's 4.2 times 10 to the 5th joules, 1 times 10 to the 5th regular calories, 100 nutritional calories, or 0.12 kilowatt hours.